Hi there, Physics 131. This is a short pre-class video for class 31. We're going to finish up chapter 10 today. So section 10.6 is called Skills for Analyzing Processes Involving Vibrational Motion. So really all it is just one example. So it's good to kind of read through it. So it's basically a long light spring is hooked to the ceiling and hangs vertically. When we hang a 0.4 kilogram clay ball at the end, the spring extends by 4 centimeters. And then it says a 0.2 kilogram clay ball rests on a table 30 centimeters below the hanging clay ball. You kick ball 1 down from its equilibrium position, determine the frequency of oscillations of the vibrating system. So she kind of goes through the idea here as a bit of a sketch. So the spring has its equilibrium length. When you attach a mass to it, there's a new equilibrium, which is this distance 4 centimeters below. And then you kick it and give it some initial velocity, and it's asking for the frequency of vibrations. So to find that initial distance where it's in equilibrium, you say that the spring force upward is equal to the force of gravity. And since what you are actually given is that distance, you can use that to find the spring constant. So you're saying that since it's not accelerating, the downward force of gravity is balanced by this upward force from the spring. So they've got the y-axis being down here. So you can solve this out for the spring constant. It's that mass 1 times g, that's the force of gravity, divided by delta y, is another ball M2 sitting way down here. So I think since the distance here is given, she wants to check to make sure that the amplitude is not bigger than 30 centimeters. Because if the amplitude of this oscillation is bigger than that, it'll hit that ball down there. So there's a whole energy thing that goes on where she says that 1/2 m1 v1 squared equals 1/2 ka squared. So this is the maximum kinetic energy when it's at equilibrium, and this is the maximum potential energy when it's at its zero velocity point. So you can solve for that amplitude. You can say that if the amplitude is greater than 30 centimeters, they'll collide. The speed corresponding to that is the initial speed is 4.7 meters per second. So if the initial velocity of the ball is less than 4.7 meters per second, then it won't have that bigger amplitude. And so you can just find the frequency use this equation, 1 over 2 pi times the square root of k over m1. So basically this is the answer. It's 2.49 hertz. And then what she says is that if it's bigger than that, then it'll collide and you'll have two masses stuck together. And so you'll have a different mass here, and it'll be a different frequency since you've got M1 plus M2 now oscillating on the spring. Although I don't know why it doesn't hit the floor actually, because that was sitting on the floor. But anyway, it just sticks, I guess. Maybe it hits it and then pulls it back up and oscillates with some amplitude less than 30 centimeters. So that's what's going on in that section 10.6. But basically, there's a few other examples that she goes through. There's this CO molecule. So this is where you're given the effective spring constant and you're given a natural frequency and you're asked to find the mass. So once again, you're using this equation. Frequency is 1 over 2 pi times the square root of k over m. And you're solving for this effective mass, 10 to the minus 27 kilograms for carbon. And the last two sections of chapter 10 talk about, I guess, like not so simple harmonic motion. So there's two ways you can modify simple harmonic motion. One is you can slow it down with friction. That's section 10.7. And then 10.8 is when you actually speed up simple harmonic motion by having a periodic driving force. So section 10.7 says including friction. So basically what happens here is that it's called a damped oscillator when you have a mass on a spring that is moving through a fluid, whether it be air or water or honey or oil. Instead of oscillating with a cosine curve, it looks like a cosine curve, but it's got a decaying amplitude. So the amplitude gets less and less with time. And that's kind of what we we are used to in real life. So there's a little talk about shock absorbers, how they work, I guess a spider web. So just a little bit about damped harmonic motion. So just as damping takes away energy from the simple harmonic motion, if you drive it with an external driving force, that can provide energy to it. So the last section of this chapter is about forcing a vibration. So for example, if you've got someone that's on a swing, you can push the swing with a periodic force of you on the child, and you can get the thing to keep going. So and then there's some talk about resonance curves. So this curve, what they're showing here, is the frequency of the driving force versus the amplitude of the motion. And F0 is like the natural frequency, I guess the simple harmonic motion frequency. So if you drive a system with some frequency that's less than this natural frequency, then it won't have a high amplitude, or more than that frequency, it won't have a high amplitude. But there's this natural, what's called a resonance frequency at 3 here, where you'll have your maximum amplitude. This is a phenomenon of resonant energy transfer. And they talk a little bit about gusts of wind at a particular period, which matches the natural swinging period of this bridge that actually causes the bridge to eventually collapse. So, and this takes us all the way back to the beginning of the chapter when there was those soldiers that were crossing this bridge. So that's an example of resonant energy transfer. If they are stomping on the bridge at a particular frequency, and that matches a natural resonance frequency of the bridge, it can create a large amplitude of oscillations, which can break the bridge there. So that's it for chapter 10, and I'll see you next class. Bye for now.